This is the current balance lab. In this experiment, we'll be using electrical current to generate a force on a wire that counteracts the weight of a mass placed on top of it. Our results will be used to calculate mu naught, the permeability constant, and in turn c, the speed of light.
This is a variable transformer. It puts out a voltage that is dependent on the position of the knob. This is a transformer. It is used to step down the voltage to help keep the currents manageable. Even so, be sure that you keep the current below 15 amps at all times. This is an ammeter. It is used to measure the current. Note that one wire should always be attached to the plus-minus terminal, and the other terminal used determines the range. For example, if you use the terminal marked 1, then the maximum reading is 1 amp.
Start by adjusting the counterbalance so that the bars are at a reasonable distance apart. You'll have to do 2 sets of measurements at different rest positions, say 0.5 and 0.7 centimeters. Ensure that the system swings freely without making contact anywhere except for the knife edges. Also, ensure that the bars are parallel, one is directly above the other, and that they are as even as possible.
Connect the circuit as shown in the lab manual. The normal transformer should be plugged into the variable transformer, which in turn should be plugged into the wall. One side of the transformer is attached to the ammeter's plus-minus terminal. You will wish to attach the other wire to the 25 amp terminal to start so that it's easy to avoid exceeding 15 amps. This wire will connect to one side of the upper bar. The other side of the upper bar connects to the lower bar. Lastly, the lower bar connects to the remaining terminal of the transformer. If the circuit is connected correctly, you will be able to see the current increase on the ammeter as you increase the voltage on the variable transformer. Note that if your ammeter is connected backwards, it will deflect in the negative direction and you won't see much.
Next, we'll aim the telescope. I find it useful to follow a 3-step process. Step 1. Adjust the focus such that you can see the objects at the distance of the mirror and aim the telescope at the mirror. Step 2. Adjust the focus such that you can see objects at twice the distance of the mirror, i.e., something near the scale, reflected in the mirror. Step 3. While looking in the telescope, slowly adjust the position and angle of the entire telescope assembly until the crosshairs are over some part of the scale. It is not necessary for the crosshairs to be at 0. You can do your measurements relative to the rest position.
Next, we'll make some measurements in order to accurately determine the bar separation. First, measure the length L between the centers of the supporting bars. Next, measure the length of the lever arm A, or the distance from the knife edge to the center of the front bar. You should do this for each side and use the average. Finally, measure the distance B from the mirror to the scale. Technically speaking, the point on the scale used should be halfway between the number you see in the telescope and the height of the telescope. Now it's time to take some measurements. Turn on the variable transformer. As you increase the voltage, you will see the current increase on the ammeter, and there will be a repulsive force between the lower and upper bars. Add a mass to the weight pan. Try not to let the bars touch. While looking through the telescope, increase the voltage on the variable transformer until the upper bar returns to its equilibrium position. Record the mass and current. Repeat this for several different masses. The range of masses used will be limited by the maximum current of 15 amps at the high end, and whatever mass will result in visible deflection at the low end.
Next, adjust the counterbalance to make a slight change to the equilibrium position, and measure it carefully using the telescope as before. As mentioned earlier, an equilibrium position of approximately 0.7 centimeters is recommended for your second set of readings. We hope you enjoyed the current balance experiment, even if it is a little ironic that the current balance lab has equipment that's so out of date.